Okay, we're doing some examples of the quotient rule. Now this is the version given in the formula book, but it's a bit of a scary looking version, so you can use it, but if we think of our function as being, the product rule was when we had a function times another function. Now we've got a function, and we normally call the top u, divided by another function called v. It's okay to use f of x and g of x. This is the answer for dy by dx, okay, but what this is actually saying is that it is u dashed times v minus u v dashed all over v squared, okay, which is fairly memorable. Okay, you have to learn the product rule. The only difference is on the top here we've got a minus in the middle instead of a plus, and then we're dividing by v squared. So I think learning this version of the quotient rule might be more user-friendly than actually working with this version in the formula book. But you have got this to turn to if you're absolutely stuck. Okay, so let's apply it. So this is my y, so this is going to be u over v. So therefore, I've got a u. Now this time, with the product rule, u and v, the order didn't matter. The order does matter from now on. U has to be the top, which is 5x plus 2. V has to be the bottom, which is e to the x. But now this should remind you of the product rule. U dashed is, differentiate this, we get 5. V dashed is, differentiate e to the x, we get e to the x again. So my dy by dx equals u dashed v minus uv dashed all over v squared, which is u dashed v, 5, times v is the first e to the x, minus uv dashed, so that's a bracket of 5x plus 2, times v dashed, which is also e to the x, all over v squared, so all over e to the x squared. And there's a bit of simplification we can do, but advice on the quotient rule is the answer can look quite untidy. Sometimes it doesn't simplify very much, and in an exam situation you may well get full marks even for the unsimplified answer. So tend not to simplify too much unless you really have to. Okay, so the one thing I would do here is the e to the x squared on the bottom I'd write as e to the 2x. Okay, now the other thing you can do is multiply out the top. So you can see I've got a 5e to the x, and then I'm going to have a minus 2e to the x. So I can see there's a 3e to the x in the top. And I can see there's also a minus 5xe to the x, which I can't combine with the other term. But I can see that this is a common factor of e to the x, and in fact there's e to the x squared on the bottom. Rather than writing it as e to the 2x, actually, I could divide top and bottom by e to the x. So I suppose the simplest form would be dividing the top by e to the x, we get 3 minus 5 e to the x. So dividing both terms by e to the x. And then the bottom, well, originally it was e to the x squared. If I'm dividing by e to the x, I can see it's just e to the x again. So that's a simplified version of the answer, but as I say, this version of the answer, even in its unsimplified form, is often good enough. Okay, now the next one doesn't look like a quotient at all. Okay, we've got y equals tan x. What we've got to do to differentiate this, differentiating tan x, by the way, you can look up in the formula book, but you can also be asked to prove what's in the formula book by thinking about what tan x is. And the formula we need, the hint is we're using the quotient rule, so it's going to be a fraction. So you should remember that tan x is sine x over cos x. So that gives me the hint that I need to take u is sine x, the top of the fraction, and v is cos x. So I can set up my u dashed, which is going to be differentiate sine x, I get cos x. My v dash, differentiate cos x, I get minus sine x. So dy by dx, okay, is u dashed v minus u v dashed over v squared. So my u dashed v is cos x times cos x. And I need to take away my u times my v dashed, which is sine x times minus sine x, all over v squared, and v squared is going to be this cos x in a bracket squared. Now I definitely do want to simplify this. So the cos x on a bracket squared, we normally write that as cos squared x. Okay, but on the top I've got cos squared x, because this is cos x times cos x, that's cos squared x, and this is a minus times minus is a plus, which is going to be sine squared x. But cos squared x plus sine squared x, I can do something with. Okay, what I can't do is cancel this cos squared x with this cos squared x. Okay, I can divide the whole of the top and the whole of the bottom by cos squared x, but that wouldn't be very nice. Okay, I can't just notice one thing that matches on the top with what's on the bottom and start cancelling. That's just wrong. So what I have to do is look at the whole of the top, and I should recognise that that is 1. So the simplification we get is we get 1 over cos squared x. And of course 1 over cos x is called sec x. So this is sec squared of x. So that's a proof of, well, the fact given in the formula book is that in your formula book it tells you, here we go, this is page 7 of the formula book. This line here tells you that tan of kx goes to, when you differentiate f dashed of x, is k times sec squared of kx. So we did tan of x, so k was 1, and we got sec squared of x. So we've kind of confirmed that result in that particular case. Anyway, this is what your quotient rule calculations should look like, okay? And this piece of advice here, you're often better off not trying too hard to simplify unless it's obvious what to do.